Hello everyone, welcome to this video. In this video, let's discuss how many subgroups of order 4 does D4 have. The answer here is 3, right? 3 is the answer. Now, what all 3 subgroups would be there? Let me show you. The first one is this subgroup R0, R90, R180 and R270. This I have named to be S1. The second one is contains H, V, R0, R180. This I am calling by S2. And the third one is D, D dash, R0 and R180. This I am calling by S3. Right? This is the answer for this question. Now those of who who are interested to know the reason of how they can continue watching this video, otherwise you may stop it, right? Okay, moving forward, we know the Kelly table for D4, right? This is the Kelly table. Now for this Kelly table, using this and using the Lagrange's theorem, which we already know that the order of subgroup divides the order of group. Here the group is D4, its order is 8. So what all divisors do we have of 8? 1, 2, 4 and 8. So that means the subgroups, the possible subgroups of D4, they would have order as either 1 or 2 or 4 or 8, right? You know what is order 1 subgroup? It is just the identity. It just contains one element, which is the identity. So this is the trivial subgroup. Moreover, you know the only subgroup of order 8 is D4, the group itself, right? Now remaining these two members, 2 and 4. Now let's discuss about them. We already know a result which states that if G is a group of order 2p, where p is some prime number, here we are talking about the subgroup. Instead of group, we are talking about the subgroup. Subgroup of order 2 or the subgroup of order 4, right? So if that is a prime number, p is a prime number, so you can write the group of order 2 as 2 into 1. You can write it 4 as 2 into 2. So 2 and 1, they could be taken into this category, right? And then this group would be isomorphic to Z2p or ZP. This is the result. So now using and applying this thing onto the subgroups of order 2, we may write the subgroups of order 2 as isomorphic to Z2, right? Why? Because Z2 is the only subgroup of order 2 up to isomorphism, and moreover, whatever subgroup we will be getting from this, that would be cyclic in nature and would be generated by an element of order 2, right? Similarly, for a subgroup of order 4, it must either be isomorphic to Z4 or it must be isomorphic to a combination of Z2 and Z2, right? So this is why this is so, because they are the only possible subgroups or groups which are having order 4 up to isomorphism, right? So we are interested in this question to talk about this order 4 subgroup. Hence we'll be discussing this case only, where we'll be talking about Z4 and Z2, correct? Z2 cross Z2. So if we are in Z4, that means we are looking for a group which is cyclic in nature and it would be generated by an element of order 4. So that means we have to look for some element X within our group such that it would give you identity, right? This is the definition of order. So if you look at your group, you see R90 raised to power 4. It would be R90 into R, it could be R90 square, R90 square. What is R90 square? R90 composed with R90, it is R180. So R180 square. What is R180 square? R180 composed with R180 is R0. So you see R90 satisfies this condition. This is R180 composed with R180 and this is R0, right? So the order of R90 is 4, hence we have one such element as R90, and the other you can simply see it could be R270, right? These would be the two elements which would generate this group which is isomorphic to Z4, right? And it would be a cyclic group, so it would be obtained by taking its power or its power, correct? So let's first of all discuss about this case. So in this case, the powers of R90 would be R0, R90, R180 and R270, correct? So the elements would be this. And similarly, when you take the powers of R270, now we can use these two results, RNM is equals to RNM. So that means first of all, we'll be taking the power 0 of R270, it is R0. The power 1 of R270, it is R 270. What about power 2? Power 2, now here we can apply this result. So we can multiply 2 with 270, it would be 450. Now we can break up 540 into 360 plus 180, right? We can do that. So now this thing 360 into something, it is 360 into 1 in this case. 360 into 1 plus 180 would give you just R180, right? So this is what I have used here. And similarly 3 multiplied with 270 is 810. 810 you can break down as 720 plus 90. Now 720 is 2 into 360. So you have R2 into 360 plus 90. So this would be R90, right? So this is R90. So you see these 4 elements are already present within this group. So this is basically equals to R270 in this particular case, right? So we obtain one subgroup S1 from it. We are calling it S1, correct? Now let's move on to the second case where we are saying we have Z2 cross Z2, right? For this we have to look for all the elements which are having order 2. So that means we are searching for the elements such that when we take its power 2 we obtain the identity elements. So this is quite obvious that we have all these elements when we look at the Calais tables. How? Let me show you. Here you can clearly see R0 into R0 is R0. R90 into R90 is not R180, so we'll not take this element. R180 into R180 is R0, right? R270 is not R0, right? So we'll discard this element. Then H with H is R0, yes. V with V is R0, yes. D with D is R0, yes. Right, and D dash with D dash is R0, yes. So that means you have to just look at the diagonal elements. Here you have R0 with you, R180 with you, H, V, D and D dash with you. These elements satisfy this condition and they are of order 2 here, right? Now out of these elements we have to look for the elements which commute with each other, right? Which commute with each other. So for that we have to find the commuting pairs out of these. We are leaving R0 because R0 would commute with each one and it would obviously be present in each subgroup being the identity element, right? So from the Calais table you can look at the pairs that R180 commutes with D, R180 commutes with D dash, R180 commutes with H, R180 commutes with V, D commutes with D dash and H commutes with V. However, D and H do not commute, D and V do not commute, D dash H do not commute and D dash V do not commute from these results, correct? Once you have obtained these 6 pairs, so that means utilizing these results you obtain 6 pairs such that from those 6 pairs you can generate your subgroups, right? So what all pairs are there? R180 comma D, right? R180 comma D dash, D comma D dash, R180 comma H, R180 comma V, H and V, correct? Now using these, first of all let's take this generating members. If let's call our second subgroup as S2, right? If S2 is generated by H and V both, then H and V would surely be there. We have to see what all elements would be obtained when you multiply or apply different operations onto this. So you see H into H is R0. So R0 is definitely present in your group. You can add it over here. We can check H into V is R180. So R180 is definitely present within your group. You can see R180 into R180 is R0, which is already present. Then you can check for V into V. It is also R0. It is already there. Then you can check for R180 into H. It is V. Then you can check for R180 into V. It is again H. So in this way you can see that all the elements, they give you now the results H, V, R0 and R180 only. So therefore these are the possible elements which are present in our group, and hence this becomes the second subgroup of order 4, right? And moreover, if you in a similar manner check for this subgroup which is generated by R180, 8 and R180, V, they would be same as this one. Hence we obtained our second subgroup from here. Similarly, for the third case, let's check the subgroup which is generated by D and D dash. So obviously they both would be there, right? What about the other elements? So you see D into D gives you R0, so you put R0 here. then d dash into d dash gives you r0. It is already there, no need to do anything. D into d dash is r180, so you put this element also there. R180 into r180 is r0, which is already there. D into r180 is d dash, which is already there. D dash into r180 is d, which is already there. Hence we have obtained our second element. There are no more combinations present, hence we stop here. Hence S3 is this another subgroup having order 4 in D4, right? And moreover, you see, if you generate the elements using this R180 comma D or 180 comma D dash, they would also be equal to this one. Hence we have obtained our third subgroup, right, of order 4 in D4. Hence the required subgroups are S1, S2, S3, which are the three subgroups of D4 which are having order 4, right? So I hope you understood this result well. Well, that is it for this video. Thank you for watching.